So, hello everyone. My name is Monu Pathak, and I am going to explain basic game theory here, and also I will explain you the simulation by how I also validate the king theory formula, some king theory formulas with the simulation also. So let's start. So, in what happens in king theory? There is a server that is a like there is a first serves a particular thing. Like in cafe, there is a receptionist or there is a receptionist and there is a customer that goes to receptionist and just take a billing thing. After food, there is a billing thing. He went to the receptionist and tell his items, then the billing happened and just he leaves the system. Or we can take it food processing time. Food processing time. So I a customer the system and when he went to the system, there will be a service time to deliver him food because food needs to be prepared, and then after eating his food, he will be leaving the system. So this is a basic queue theory. So now I am going to explain MM1Q. So MM1Q is basically Markovian Markovian arrival, Markovian processing time, and one server. Like I don't need to have more than one receptionist. So also the capacity of the system needs to be infinite for this formula that I am going to explain. So this is my server, this is my queue, and this is my layout. So what happen usually, I take some random values as my inter-arrival time. Inter-arrival time is the duration of time between two arrivals, and service time, and this let's I only need these two values. So as I already said, these two needs to be exponentially distributed with some mean. So this can be of different mean m1 and this can be of different mean m2. So let's take interarrival time is with mean exponentially distributed with mean 10 minutes. First customer comes at 8 minutes and then other customer came at after 8 minutes. Other customer will come at I think 3 minutes. Then 4, then this would be third customer, and then 2 and 5, and this will be 4, 3, 9, 2, likewise. So, to explain this interarrival time, I will show you. First customer will come at the arrival time of 8 minutes because from 0 to 8 this is the duration. Then other customer will came at the instant of 11 minutes because 8 plus 3. Then other the third customer will came at the instant of 13 minutes and then 18 minutes instant. So as this is it. Then when first customer came C1, it was 8 minutes in clock. Clock was banging on 8 minutes. Then it served 4 minutes and it leaves the system. So 8 plus 4 at the instant of 12 minutes he leaves the system. Then C2 comes. C2 came at 3 minutes I think. So so when he was busy, this system was busy. C2 came, and C2 came and wait for 1 minute, and then its processing starts at 12 minutes, and it leaves the system at 12 plus 3, 15 minutes at the instant of 15 minutes, and then C3 came. When C3 came, It was already 13 minutes. Then system was busy. So my server was processing C2. So it wait around 2 minutes, and its processing began at what we can say 15 minutes, and it served a 9 minute long duration in the system. Duration. I'm saying duration. So I'm not saying instantaneous time. So it served a 9 minute long duration. So its instantaneous time when it leaves the system was 9 plus it is 24 minutes. And so as for others. So now I think you are able to understand it. So there is a nice formulas for queue theory, like utilization, average server utilization. So the server utilization is generally for infinite. So I am taking this queue of having infinite size. So like my any number of customer can wait, not one, not two, not three. Infinite number of customer can wait. So my utilization is having very good formula. It's basically hmm, it's service time upon inter-arrival time, or I can say it as inter-arrival rate. Arrival rate upon service rate. Service. So service time was uh, time taken by an item. So I'll just explain it. It was time taken by an item to process. So my service rate will be mm, how many items will process in unit time. Interval rate will be, and so as interval rate, my interval rate will be how many arrivals, in unit time, and my interval time was number of arrivals. Uh, my interval time was time taken by an arrival, time taken for an arrival, time taken for an arrival of entity, time taken to arrive by a unit arrival, or by a one entity, and it is just opposite. How many arrivals are there in unit time? It's just opposite of it. So this is it, and these two values are absolutely same, absolutely same. And then there is the average time in system. So average time in system, I think it's 1/mu minus lambda. So this is average. So mu is basically my service time, and lambda is my service rate, my inter-arrival rate. Now, these two notations are really important for simulation, for queuing theory. Hmm, This is very important for these two. Now, we just went to our simulation. So, for this, let me give you some better. Wait, let me open my calculator. Hmm. I just created a, thought that it was not useful, but I just wanted to share it with you now. So, like here, I have made some arrival of some entities. Let's see. So yes, so like my A is a randomly distributed value with mean 3 and 10 values are there. And B is my randomly distributed values with mean 5 and 10 values are also there. So just I wanted to share one thing. So this will be, so my interval time would be like this for customer at index 0. So customer 0, interval time would be this. Customer 1 would be this. Customer 3, 4, 5, 6 would be this. And processing time would be this. So also I can say if I want to explain it with respect of time only. So at the instant of 2 minutes, my first arrival happened, or my zeroth arrival happened. And instead of approximately 6.2 minutes or 6.1 minute, 6.2 minutes or something, my second arrival, my first arrival happened. One arrival happened. Then second arrival by adding that value, the clock value to this and to this to this. Actually, I wrote the formula. I'll write it again. So, yeah, it is it. This is it. So, yeah, I just have to run it. Okay. And DF is just a data frame. Don't bother about it. We're not gonna use it. So yeah, you can see for my zeroth person, the time of its arrival was this. At this instant, it arrived. My first person arrived at this instant. Second person arrived at this instant. So as for third, fourth, fifth, sixth, and for 10th, for ninth. Yeah. So just we'll go to my simulation. Mhm. So I have used a SymPy module here to simulate the values. So yeah. So my inter-arrival time is 1 minute. My service time is zero point 0.5 minutes. I'm just taking random values. I'm not thinking about too much because the ratio will be, you can get the ratio of what. And this is my function to generate interval, that is np.random. This will give one exponentially distributed value with mean this. And this will give one exponentially distributed value, this function will mean this. So yeah, you can see I have just made the cafe. I don't want to show you type 1, type 2, type 3 customers. Leave it. Just I made a cafe, and whenever a arrival happened, I just print customer arrives when the server is free. Because it is when I am getting the request, I am requesting the server, and whenever server is free, that then only he will accept my request. Then I am noting his time, its time when the server got free, and also I am noting the time for noticing the time for arrival when arrival happens, and that value, that this value, this value, yeah, I am noticing this value also. Okay, I just created one more column by running it 2 times. Hmm. So I am noticing this value for each arrival, this instantaneous time. Uh, do this. Then what's then customer is being served, and when customer departs, I am also noting that time too, and I just say like customer depart with this time, and that's it. That's approximately it. That's it. Huh. I just ran this simulation right now only. Yes, yes, yes. So first arrival happened at this time, it's point 0.1 instant, and customer one arrived. It is being served because server was idle. Because initially server was empty. Then it processed the item and customer leaves. When customer two arrived, it is being served. When the customer two was being served, customer three and four also arrived. You can see, and they are waiting in queue. And when customer two departs, customer three starts start serving for customer three is being start. And when customer three departs, customer four. And you can see when the customer four was being served, The system was busy to arrival again happened. And when customer five parts, five is being processed, six is being processed, and so on. Then I was just putting these value into a list, right? And these values, the TD parts minus busy. Like when my server starts serving my customer for customer one, and when it's leave, difference of both, I'm just putting it into it, putting that value into this utilized. And for customer two also, I'm putting this value and appending it to the list. And for customer three and customer four, how many customers that I can serve, I am putting these values. And so as for waiting time, this is waiting time for system, not for a queue. This is waiting time for system. So yeah, you can see where this arrival when system when an entity or when a customer arrived. So I'm just taking the duration of it, and because we need to have a duration, then I just wanted to show a very good thing, very crazy thing. So this is uh, so lambda is my arrival rate. This needs to be arrival rate. Sorry, inter- this needs to be so lambda is my inter-arrival rate. Mu is service rate. Utilization I am showing it as rho. It is inter-arrival rate upon service rate. Like we can also say it as service time upon inter-arrival time. Both things are same. And then waiting time in system is 1 upon mu minus lambda. So I'm just showing those values to you. Yeah, you can see my simulated utilization is because I am taking the sum and just dividing it to the simulation length. So, or I can say that how many the duration of which for which my system was busy. I'm taking some of it, like for 2 minutes it was busy, then for 5 minutes it was busy, then it was enjoying for 3 minutes, it was taking rest, then it was busy. So I'm not calculating the resting period. I'm just calculating the busy time for our system or for our server, and then dividing it the total simulation length. Here I have taken it 100 minutes, so I'm dividing it with 100 minutes because total time cannot pass 200 minutes, cannot surpass 100 minutes. So you can see my utilization is nearly equal to zero point 0.5 or 0.51, I can say. Yeah, and average time in system is just just equal to 0.94. It can be one. We can take it as one. And what you can see here is my utilization, arrival rate upon service rate is also 0.5. Yeah, you can see it. And when we calculate 1 upon mu minus this will be 0.5 upon 0.5. This I think it is not correct. Just have a look at the utilization rate as of now. You can see utilization is zero point 0.5 and it's correct. So this shows like my game theory is correct for game theory is predicting correct values for for our system. And yeah, there are various formulas in game theory you can see about it. And I just explained very few things. So thank you everyone. This was Mono Pathak, and I'll see you in other videos. Thank you.